Greetings, folks. The periodic arrangement of the elements into what we now know as our periodic table was a fantastic discovery, which led to even more experimentation and questions. What was the underlying reason that leads to this organized arrangement of the elements and their reactivity? Further experimentation had also led to the discovery of ions, charged atoms, and radioactivity. Now, how can these phenomena be explained if atoms are truly indivisible? The periodic table's interesting structure baffled scientists for quite a few years and required extraordinarily elegant experiments to guide us to an understanding of the true nature of atomic structure and the factors that govern atomic reactivity. In the 1870s, Sir William Crookes, an English scientist, developed cathode rays in a vacuum tube, but nobody was sure what the rays were. In 1896, another British physicist, J.J. Thomson, found that these cathode rays were negatively charged particles because they were attracted to positive charge and repelled by negative charge. He called these negatively charged particles electrons. By deflecting the stream of particles with a known charge, he was able to figure out the mass of the electron relative to its charge, which we call the mass-to-charge ratio of an electron, which is simply the mass of the electron divided by the charge of the electron. Later in 1909, the great American scientists Robert Millikan and Harvey Fletcher ionized oil drops, loading them with negatively charged electrons. They were able to suspend the drops between charged plates by varying the potential between the plates, thus determining the total charge of the electrons on the drop. They assumed that charge must be an integer value of the number of electrons times the charge of a single electron. From their results, they were able to extrapolate what the charge of a single electron must be. The charge is equal to minus 1.602177 times 10 to the minus 19th coulombs, where coulombs becomes a new base SI unit for charge. Knowing the charge of the electron and Thomson's mass-to-charge ratio for the electron described on the previous slide, the mass of the electron was calculated to be 9.10938 times 10 to the minus 31st kilograms. It was a bit shocking to the scientists of the day to find a particle having a mass almost 2,000 times less than the smallest piece of matter known at that time, the hydrogen atom. In 1886, Eugene Goldstein discovered anode rays, also called canal rays, which were shown to be positively charged particles produced from gases. See, since the discovery of electrons, it was surmised by many scientists that there must be a positive entity present in atoms to offset the negative charge of the electrons. In 1899, one of J.J. Thomson's greatest students, the New Zealander Ernest Rutherford, discovered that there were three types of radiation emitted from radioactive elements: a rather large positively charged particle called an alpha ray, which we would find out is actually a helium nucleus; a negatively charged beta ray, which was discovered to be a high-speed electron; and a gamma ray, which is high-energy light. In 1911, Rutherford was able to create a focused, positively charged alpha ray gun. He focused the alpha rays at a very thin film of gold. He found that most alpha rays went directly through the film, but there were many rays that were scattered at drastic angles. Now, the only way he could make sense of the results was to assume the atoms that made up the gold element were mostly just space, but there must be a very small positively charged core to the atom that could strongly repel the alpha rays. From these results, he was able to develop the nuclear theory of the atom. Now, here are the tenets of this theory. The atom's mass and its positive charge are contained in a tiny core called the nucleus. The tiny negatively charged electrons travel about the nucleus, so the volume of the atom is mostly empty space. Materials are naturally charged neutral, so there must be just as many positively charged particles in the nucleus as electrons traveling about it. These positively charged particles he called protons. This recognition of the nuclear atom is why Rutherford is usually attributed to the discovery of the proton. So the charge of a single proton is equivalent to the charge of the electron except opposite in charge, 1.602177 times 10 to the minus 19th coulombs, and the mass of the proton was calculated to be 1.67262 times 10 to the minus 27th kilograms. Rutherford and others noticed that the proton and electron masses could not account for all the mass in the atoms of the known elements, so he proposed that a neutral particle may exist in the nucleus. These proposed but yet undiscovered particles came to be called neutrons. A British scientist, James Chadwick, looked for the elusive neutron for more than a decade, and finally, in 1932, managed to produce and identify it by shooting an alpha ray at the element beryllium, which then emitted this wonderful new particle. The neutron obviously has no charge, and its mass is slightly more than the proton. It's 1.67493 times 10 to the minus 27th kilograms. It was surmised that in the nucleus is where most of the mass of the atom is located, and must be where the neutrons and protons reside. This newfound knowledge about atomic particles led us to the fundamental foundations of the true nature of matter. First, what makes an element and makes them different from all the other elements on the periodic table? Well, the answer is the number of protons. A specific element is made up of atoms that all have identical numbers of protons in the nucleus. The atomic numbers on our periodic table actually mean something. This atomic number is equal to the number of protons in the nucleus of an atom of a specific element. Now, a second question that can now be answered involved the nature of atomic ions. Ions were discovered earlier in 1834 by the great English experimentalist Michael Faraday while doing electrical conductivity experiments. He surmised that ions were charged particles of matter of two types: positively charged particles, which came to be known as cations, and negatively charged particles, anions. Now, what was the source of the charge in ions? Well, now we know the answer based on our new atomic theory of the arrangement of particles within the atom. Cations are a result of the atoms in the substance having more protons than electrons, and anions are atoms that have more electrons than protons. Thus, ions exist when there is an unbalanced number of electrons and protons within the atoms of the substance. So let's say the particle is a halogen atom, like chlorine, Cl. The halogens are the second to last column on the periodic table. And typically, halogens love electrons, and the atom will usually find no problem stealing one extra electron from some other unsuspecting substance, becoming an anion. This behavior is also why this group of atoms, halogens, are so reactive. So the general reaction scheme for a neutral chlorine atom gaining an electron is shown. Notice how the neutral element is expressed with its atomic number as a subscript, and the electron is a particle and its singular charge expressed as a superscript. The result, the chlorine atom absorbs the electron and gains a negative charge, becoming a chloride anion. This new Cl atom maintains 17 protons but now has 18 electrons. Now, it's important to note here that for regular chemical processes, atoms do not change their number of protons or neutrons, because if they did, they may no longer be the same element anymore. The types of processes where the number of protons and neutrons change and are transferred between entities in the reaction are called nuclear changes or nuclear reactions. Now, the new Cl atom, anion, is called a chloride to denote its difference from the neutral Cl atom that we call a chlorine. We also like to say that in this electron transfer process that the chlorine atom has been reduced, and the process of a particle gaining electrons is called a reduction. We'll do more with this concept later. This reduction process is typical behavior for all these reactive halogens and is the main reason why you will not find neutral halogens in nature. They are almost always found in their reduced form within chemical substances. Now, the alkali metals are also very reactive elements. Now, these elements make up the group or column on the far left of the periodic table. Now, in their case, they love to give away one of their electrons to other materials. The general reaction mechanism for an alkali metal such as potassium K losing an electron is shown. The positive K atom is the cation and now has only 18 electrons and 19 protons. These cations do not have any special names like the halogen anions do. We say that the neutral potassium atom has been oxidized, and this is called an oxidation process. The periodic table on this slide shows elements that tend to form very predictable ions. Now, we need to be very familiar with the common ions in this table. Now, notice the charge of the group 1A and 2A metals on the left, and the main group elements on the right and their placement relative to the noble gases. This observation leads us to a general chemical rule. Everyone wants to be noble. It looks like most of the ions in these groups want to have the same number of electrons as their nearest noble gas. The halogens are gaining one electron, so they have as many electrons as the noble gas on their right. For example, chlorine, which has 17 electrons, wants to gain an electron, so it has as many electrons as argon, which has 18 electrons. The alkali metals want to lose one electron to look like the noble gas equivalent. K, potassium, has 19 electrons and it loses an electron, so it has 18 electrons, just like the noble gas argon. Now notice all the alkaline earth metals in the second column from the left are losing 2 electrons to have as many electrons as the nearest equivalent noble gas. This pattern is remarkable and a pretty significant observation. We see that what makes an element is the number of protons, but what dictates the reactivity and periodic arrangement of the elements is the electrons. We are now getting to the very heart of chemistry, electronic structure. Catch you later.